Okay, we're going to continue on. We've been talking about kind of transition metals a little bit here. To begin this sort of chapter, we're going to go again over some more properties of them and some trends. And again, it's really because of the heart of this chapter, which is about coordination compounds and complex ions. They typically have these transition metals as the sort of core of them in the center. So a reminder, as we talked about, obviously transition metals have multiple oxidation states. They also obviously are, in terms of electron configuration, the d orbitals are involved, especially the first row transition metals. And as we, I think, finished up on last time, we were sort of talking again about electron configuration. And remember that, if you had something like iron, which is 26, you have argon 4s2 3d6. And when transition metals get electrons into the atom and are filled, the normal sort of order, like you would write electron configuration, is that they do fill the S first and then start to fill the D. A reminder that once that occurs, there's actually, again, a sort of a switch in the energy of those orbitals. And what ends up happening is the 4s, for example, in this case, ends up being higher than the 3D. And that's really important for when they lose electrons. So transition metals always will lose their s electrons first, and then they will dip into perhaps some d electrons if necessary. And that's a little bit different than representative metals that always sort of lose the sort of last ones in electron configuration and end up at noble gas configuration. Transition metals typically do not. So you could also figure out valence electrons by the group number. And when we are talking about sort of the transition metals, we got Sc and then right around here, iron. And we kind of go the traditional sort of numbering 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 down to zinc. And these are basically technically the amount of valence electrons that each of these guys have. For example, iron here would have the 2s available to them and also the 6 in the D. Not that it probably will ever lose all 8 of those, but it does have them sort of available to them. Any questions on any of that stuff there? All right, so kind of continuing on with a little bit more about transition metals. As we know from our sort of redox experiment, especially with the Mn, these guys can make a wide variety of sort of oxidation states. Remember that oxidation states and oxidation numbers, as we talked about, is not necessarily the sort of charge we think of on some of these guys when they are in an ionic compound. But something like Mn, as you had from that list that was in the lab, it could be a variety of sort of oxidation states. I would say the vast majority of them are, as you can see, kind of +3s and +2s are very common oxidation states. But you can kind of see as you go down the first period there of transition metals, the first row, oxidation states sort of peak at Mn and then, sort of work their way back down as you go through here. But again, 2s and 3s, very common sort of oxidation states for our transition metals, but they obviously can do more. Another really important sort of property is ionization energy. And a reminder that the ionization energy is the energy required to remove an electron from the gas state. The general trend in ionization energy is increases as you go up to the right, decreases as you go down. That's the first ionization energy sort of theme. Now, electrons, when they are lost, and we think about ionization energy, we usually think about it in terms of cations, as those are what happens when you lose an electron. So electrons do come off, by the way, as you hopefully know, one at a time. They don't all just come off at once. So For example, if we took something like magnesium, the first thing that would happen is it would lose one electron. Then that energy required to do that is what's known as the first ionization energy. Then the guy that's lost one electron will then lose another electron. The energy required to do that is what's known as the second ionization energy. And that process would continue, for example, this guy that's lost two electrons would maybe lose another. And that would be, say, the third ionization energy. So as electrons come off, it does get harder and harder to remove more electrons. So if you just think about it logically, when you lose an electron, the overall size of that atom shrinks because it loses some of its electron clouds. That now brings everybody closer to the nucleus and is going to be held tighter. And it's going to take more energy to remove another electron. Another electron gets removed, gets smaller, and again, going to kind of continue to take more energy to do that. So the general trend is, as we can see, first ionization energy is smaller than the second, and that is smaller than the third, and et cetera, depending on how many electrons you're basically popping off. And we can see that, for example, if we look at magnesium, and again, the electron configuration, for example, for magnesium is neon 3s2. Magnesium is group number 2. It has 2 valence electrons. The rest are core electrons. So you can see that the first electron to pop off, 735 kilojoules per mole, not too bad. It gets twice as hard to remove kind of the second electron there in magnesium is about 1400 kilojoules per mole. And then we get a pretty significant jump in energy here. If you try to remove that third electron, that's about, I don't know, 6 times the amount of energy, somewhere in that ballpark, or 5 or so. And that is because as soon as we lose those 2 electrons, we're now into core electrons. And good luck trying to remove those. It's just not energy efficient. Those electrons have now been moved really close to the nucleus. They're going to be held tighter, and it's just not energy efficient to do so. That is why when we think about magnesium as group 2, it has a +2 charge. It doesn't really go this way because it doesn't take out those core electrons. It's just too much energy to do so. Same thing, look at sodium. +1, which means it usually only loses 1 electron because it's about 495 kilojoules to remove the electron in sodium. When you want to remove its second electron, which is a core electron, it's about 10 or 9 times the amount of energy to do so. Again, not energy efficient to do that, and it doesn't happen. So that's why certain elements have fixed charges, certain metals have fixed charges, because you could only really energy-wise kind of get enough there to remove those valence electrons. But once you jump into the core electrons, it's a huge amount of energy. That, for example, aluminum is a +3 because you can see the jump from the third electron to the fourth electron. It goes from 2,700 to like 11,000 or so in terms of energy. So it's not energy efficient to do so. And that's why aluminum has a fixed charge +3 as well. It'll be able to remove those valence electrons. It gets harder and harder as you go through it, but it gets extremely unreasonably hard to try to rip off those core electrons at that point. Any questions on that there? So here's some properties here of the first row transition. Everything on this page. I'm just kidding. Electron configuration. We do see overall size decreases as we talked about last time. Also, ionization energy, again, increases as we go to the right and also increases as we go first, second, and third. Common oxidation states, as you can see, mostly 2s and 3s. And density gets slightly larger as you go to the right. Mass gets more, and volume gets a little bit smaller as you go to the right because it's a smaller element. Here's some dots showing the difference between first and third ionization energy, and you can see there's a tremendous difference between taking off that first electron in terms of energy and that second or third electron as you go through there in that picture. Electron affinity is another sort of property that you probably should be familiar with. And electron affinity is basically the energy change that occurs when an atom accepts an electron. So that's kind of the energy change when an atom accepts an electron. In general, trend is it usually will increase as you go up and to the right, decrease as you go down. Electron affinity for something means you usually like it or you're good at it. So it usually means that something with high electron affinity has a very good tendency to want to gain electrons. So it's able to gain electrons. Something with low electron affinity has a lesser chance of gaining electrons. Electron affinity is usually thought of when we think about anions because they gain electrons, become negatively charged. It should not be confused with electronegativity, right? Electronegativity is different. That's the ability of an atom to bring electrons towards itself. So those are different things. Electron affinity has to deal with the energy change that occurs when they gain electrons. Electronegativity is the ability for something to bring electrons near itself before perhaps it gets gained. It's not a perfect trend, as you can see here, going up group 7, it kind of goes up and then comes a little bit down there where you get near fluorine. But the overall general trend is, again, kind of increasing to the right, decreasing left. As you also know, hopefully electronegativity increases as you go to the right and decreases as you go to the left, with fluorine being the most electronegative element that you could have. All right. This is a table of reducing abilities of first row transition metals. And we can see that greater reducing ability occurs up here. And remember that reducing ability is something that gets oxidized, right? Like uh, a reducing agent in that case. And so you may say, why is this one the one most likely to be oxidized when it is more positive? But what we're looking at here are not SRPs. These are SOPs, standard oxidation potential. They're oxidation reactions. They're not reduction reactions like we saw in our electrochemistry one. So we know if we flip these equations around, right, and write them as SRPs, that means that each of these signs would flip around, right? If we reversed each of those reactions, and now the most positive one is actually down here, and that's the one most likely to be reduced in this case, right? In that case. So again, because those are standard oxidation potentials, that's why the more positive one is actually the one that gets oxidized in this case. All right, so here's what the first row transition metals look like in case you need to spot them in a lineup or something, I suppose, right? All right, there's stuff that you don't need to do because we don't do those experiments anymore, so don't even worry about it. All right, we'll just kind of cruise through that. All right, so let's get to now really the heart of the chapter after we hopefully talked a little bit here about our transition metals. And that's really coordination compounds and really complex ions, which is part of a coordination compound. So first off, a coordination compound typically consists of two things. It consists of a complex ion and a counter ion. You could think of, for the most part, a coordination compound as really being an ionic compound. And that is because you could have two things. You could have a counter ion and a complex ion. And the counter ion could be positive and the complex ion could be negative. So coordination compound together will really be like an ionic compound. You could also have the opposite, which is you can have a complex ion that's actually positive, and you could have a counter ion to balance out the charge that is negative. So like the counter ion is really there, if you want to think about it, to create an ionic compound and just to balance out the charge of your complex ion. So complex ion could be positive overall, could be negative overall, and you could have obviously the opposite there in terms of counter ion could be positive or negative. By the way, in a coordination compound, it is usually written like a traditional ionic compound, which means the positive guy goes first and then the negative guy goes second. And that goes both for when you write the formula and also when you name it, which we'll talk about as well. So what is a complex ion? A complex ion is basically a metal in the middle that is positively charged and is bonded to one or more molecules or ions. And those molecules or ions are what are referred to as ligands. And ligands are those Lewis bases that we talked about. A reminder again, Lewis bases actually donate a pair of electrons. So things that are good Lewis bases and good ligands are things that are typically polar and have non-bonding electrons. And that allows that sort of separation in charge and those electrons to be shared. Also, really good ligands are things that are negatively charged. Because as you may know, right, the only way you can become negatively charged is you have to gain electrons, which means you got extra electrons to sort of give because you have more than maybe you should have to start with. So things that are negative, things that are polar, got non-bonding electrons, are really good ligands. So things like water as a good ligand, it can use its non-bonding electrons there on the oxygen to donate. The nitrogen here and ammonia is really good. Obviously, the chloride here is negatively charged, and we got some obviously non-bonding electrons there in carbon monoxide. The metal in the middle is positively charged, which means it's a really good Lewis acid. And Lewis acids are things that accept a pair of electrons. Why the metal ion is a good Lewis acid is because basically it is electron deficient. That's the only way it becomes positively charged. It had to get rid of the electrons, missing some electrons. So when we think about complex ions, we really think of it as like a Lewis acid base sort of situation that's occurring. We got these ligands that are donating electrons to these sort of electron deficient metals that are going to accept them, and they come together. So for example, here, if we look at our cobalt in the middle, which has a charge or positive charge, it's going to be able to accept basically electrons from the nitrogen here in ammonia in each of these cases. It will also be able to accept some electrons there from each of those chlorides. And all those guys are what are Lewis bases and are obviously metal there in the middle. So when we look at a complex ion, we oftentimes want to talk about and think about what is referred to as the coordination number. And the coordination number is the number of atoms that are directly attached to the metal in the middle in the complex ion. Now, it is how many donor atoms there are. So for example, if we look at the one on the previous page there that we were looking at there, the nitrogen here in each of the ammonias is where the connection is going to be. So basically we're connecting through the nitrogen, through the nitrogen, through the nitrogen, through the nitrogen. And obviously here there's just the chlorine, which is where we're connecting. So we basically have 6 connection points there, 3 nitrogen atoms bonded in and 2 chlorides. And the coordination number for this guy would be 6 in this case because of that. Now, sometimes people, when they like see a formula like this, and you know, they got something like this, that, and whatever the charge may be, we'll just go +1. And they'll go, okay, it's 4 and 2, so the coordination number here is going to be 6, and they just sort of add up what's there. And that's not always the case. It is the case in this case because when we look at ligands, there are different types of ligands. And what I mean by that is there are some that are referred to as being monodentate, or sometimes referred to as unidentate, and mono means one. And that is something like water and ammonia. They can only bind to the metal, if that's the metal, through the one atom each. So basically for every water molecule that you get, you get basically a 1 for the coordination number for as many as you have. Same thing for the ammonia, as they could only bind one place per molecule. Ethyl endyl diamine is what is referred to as a bidentate ligand. It is also, by the way, abbreviated a lot in this chapter as EN. So if you see just parentheses EN, that is ethyl endyl diamine. And that one has the ability actually to bind in a couple of places. So for example, if I remember what it sort of looks like, we'll go with this. Organic throwback here. So that is ethyl endyl diamine here. And if you draw it, you can see it actually has 2 nitrogens. So when you have one of those guys involved and you have a metal ion there that's positively charged, each of those guys can bind into the metal. So you get kind of a 2-for-1 deal on that. So for every 1 molecule of ethyl endyl diamine, you get 2 bonding points and 2 atoms that are bonded. So for example, if you had a metal and you had that En and 2 of them there, right? The coordination number in this case would actually be 4. And that is because if you drew another one of these, 2 molecules of that will give you 1, 2, 3, and 4 places of attachment to the metal. So it's not always, and sometimes people fall into that like, oh, it's just like the little number on the bottom. When you look at the formula, that's the coordination number. And it will be if it's monodentate, but if it's some type of bidentate or polydentate type of ligand, it will not always be that bottom number. So I would say ethyl endyl diamine is a very common bidentate. Another very common bidentate ligand is our friend oxalate. And if you draw oxalate, looks something like this. And oxalate, if you have 1 molecule of oxalate, can bind to a metal through both of the single bonded oxygens, which also gives you a 2-for-1 deal when you have oxalate involved as the ligand. So I would say those are probably 2 of the most common bidentate ones that you'll come across, oxalate and ethyl endyl diamine. So you got to kind of double the coordination number for every one that you have because you're getting 2 binding points per ligand. Now there's some that's crazy. It has 3 or more type of binding spots per molecule. EDTA actually will bind in 6 places per 1 molecule. So if you have one of those EDTA molecules, we'll see a picture of it in just a second. It has 6 different spots on that 1 molecule that can bind. And that's why it's used a lot to basically gobble up metals, because it will just surround it and stuff. If you look at in labels or ingredients on certain products, you'll see something EDTA listed a lot of times, and that's just something to sort of grab up metals and stuff like that. Now, how do we know typically how many ligands will attach to a metal? And it is roughly a lot of times based on sort of the charge of the metal. So typically, if your metal in the middle there has a +1 charge, you're probably looking more commonly at a coordination number of 2 or 4 sort of attaching. If you are a +2 charge, you're probably going to get into the kind of 4 and 6 sort of ligands attached. And if you have a +3 charge, you're most likely going to be 6, except if you're gold, you're most likely going to have 4 things attached to it. So the idea here is obviously as the charge increases on the metal, it becomes more and more electron deficient, which means it could handle more electrons being accepted from ligands. So that's why things with a +3 charge could allow up to like 6 things to attach in, because it's pretty strongly electron deficient and it has room to sort of accept those electrons are coming in, as opposed to something with a smaller charge probably hasn't lost as many electrons. It's not going to have perhaps a lot of room to let those guys come in. I drew it correctly. That's good. That's ethyl endyl diamine there, which again is a bidentate. This, by the way, is EDTA. And as you can see, it actually has 6 places of attachment. 1, 2, 3, 4, 5, and 6 right there. So one molecule of that EDTA is just going to gobble up a metal pretty much all around and surround it. And bidentate and polydentate ligands are sometimes referred to as chelating agents. And a chelating agent is pretty much just that. It will basically surround metals and sort of encase them and keep them, allow you to take them out or not allow them to be freely floating around. All right, so here's a table of some common ligands, and you got some similar table in your book. Again, our unidentate or monodentate, water, cyanide, ammonia, nitrite, hydroxide, thiocyanate, and the halogens, so Cl minus, Br minus, all those guys. There's our 2 common bidentates, our ethylendyl and our oxalate. And this is diene, which is diethyl endyl triamine. Triamine means it has 3 nitrogen groups. These are in organic chemistry amines, basically. So that's where that name comes from. And here is our EDTA, our ethyl endyl diamine tetraacetate. That should be like an extra credit to spell that, perhaps. And again, there's just 6 spots where it could do it. It actually has a minus 2 charge there going on, or minus 4 charge, as we have negative, 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 and negative sort of happening there in that particular case. All right, so once you take a moment here and determine the oxidation numbers of the metals that are in the complex ion. By the way, when we look at something like this, typically the complex ion is the one that is found in the brackets. So typically in the bracketed part is the complex ion. So take a moment and decide what is the oxidation number of the metals that are in that complex ion. Okay, so let's take a look at it. So starting here with the first one, which is this here. Once again, the one in bracket is typically our complex ion. By the way, that does mean that the guy in front is actually our counter ion in this case. So if we look at this, we could assign oxidation numbers to our gold. That is OH in parentheses. That's hydroxide. That's a -1 for the hydroxide, and there's 4 of them, which gives you like a -4 happening. The potassium is the normal charge of potassium, which is +1. So that is a -3. That means that the gold here is going with a +3 oxidation state. Yeah. Any questions on that there? Now, if we look at our second one here, we got this. Once again, here in our bracket, there is our complex ion. And that would mean that this guy is our counter ion, actually, in this case. And we could do the same thing. Ammonia is no charge, not ammonium. That's ammonia. That's NO3, which is nitrate. That's -1, and there's 3 of them, gives you a -3. That means here our chromium will be going with a +3 oxidation state. First off, any questions on that there? So if we look at each of these things, right, and we just take our complex ion by itself, and we go with our AuOH4, the charge on the complex ion by itself, without its counter ion, is we just figured out the gold is +3, this is -1, and there's 4 of them. So -4 and +3 means that this complex ion overall is a negatively charged complex ion, and it has a -1 charge overall. Yeah. That is why when we look at our counter ion in this case, like a normal ionic compound, we want it to equal 0. we just need one potassium ion, right? So +1 -1 gives us a coordination compound that has no charge. Any questions on that there? Same thing if we look at the one on the right here and we just pull out the complex ion part. The ammonia is 0, and we figured out the chromium is +3. So really this complex ion here has a +3 charge, so it's actually positive complex ion in this case, as opposed to our guy on the left there that's a negative complex ion. That is why when we look at our counter ion, which is our friend nitrate, which is NO3 minus, we need not one, we need not two, but we need three of them to balance out that +3 charge that's here. And again, that is why we have three of them in this case. So these two are really good examples of what we were talking about at the very beginning here, that you could have a complex ion that's negative and a counter ion that's positive to balance it out. Or in like the second case here, you could actually have a positive complex ion and a negative counter ion to balance it out. Any questions on any of that there? Okay. So then let's get to the fun part. Let's see. And let's talk about naming coordination compounds. I know at this point you felt like you've learned to name everything, but there's more. So we'll start with our coordination compounds. So as I mentioned before, you can think of them as an ionic compound. And just like in an ionic compound, you always go with the positive guy first and the negative guy. Again, that works the same way here. We want to go with the cation that's positive first, the negative anion second. Again, both in really the name and sort of the formula as well. Within the complex ion, we name the ligands in alphabetical order, regardless of any prefix that may be there. So we may sometimes use a prefix if we have multiples of the same ligand. So regardless of the prefix, we use the beginning part of the name of the ligand. Now, some of these negatively charged ligands will end with O. Some neutral ligands will be called the name of the molecule. There are some exceptions. Water is aqua or aqua, depending on what book you got going on. CO is carbonyl. NH3 is amine. Now, if we do have several ligands of the same guy, like for example, we have two chlorines, we do use prefixes like di for 2, tri for 3, tetra for 4, penta for 5, and hexa for 6. So again, we can use these prefixes depending on how many of each of these ligands we got going on. So if you had two chlorines, it would be dichloral. We do name our halogens, by the way, chloral, fluoral, iodo, and bromo, kind of like what they do in organic chemistry. So that's how these guys are named as well. Now, to complicate something sometimes is if the ligand itself already has a prefix in its name, then if you have multiples of that ligand, you don't use di, tri, or those guys. You use bis for 2, tris for 3, tetrakis for 4. So again, if it already contains a prefix in its name, you roll with these guys as it. What's an example of that? It would be our EN, for example, our endyl ethyl diamine. So because in the actual name it has that diamine part of it, you would then use, if you had two of them, bis, or if you had three of them, tris, with that particular ligand. So if the ligand itself has a prefix in it, then you'd go to those other guys. I will say that it's also oxalate. Very commonly people use these sort of prefixes for oxalate, even though its sort of name doesn't necessarily have a prefix in it, but that's very common. People use those prefixes for it. The oxidation number of the metal is written in Roman numeral. And it always comes as the last part of the complex ion name. So the metal that's in the complex ion always comes as part of the last part of the complex ion part of the name. And I say that because it is not the last part of the name. It's the last part of how you name the complex ion part. So remember, the complex ion part could be positive or it could be negative, which means if it's positive, then the name for the complex ions can come first. And that metal part will come after all the ligands at that point. If your complex ion is negative, then it will come pretty much at the end of the name. Now, we do use Roman numerals, and we do use Roman numerals with these guys for some things that we normally do not use Roman numerals for. So, for example, zinc, cadmium, silver, we normally don't use Roman numerals when we name them because they have fixed sort of positive charges. But here we actually do use Roman numerals for those guys. So we always sort of use a Roman numeral when we're naming these type of guys, even if it's something that has sort of a fixed charge and we don't usually put a Roman numeral. The other kind of weird thing that they do with these guys is, as odd as it may sound, you could have a neutral metal and we do kind of put a 0 there in terms of that. So you could have a guy that has kind of no oxidation state or 0, and we do kind of put a 0 in there, which is not technically a Roman numeral in that case. Now, lastly, the interesting part of this one is if your complex ion is negative, then we actually roll with the kind of old school name for the metal, and that was usually end with 8. So instead of copper, we go cuprate. Instead of iron, we go ferrate. All those ones that maybe you learned when you were talking about type 2 and the Roman numerals, the older way of naming metals, we roll with those type of names if the complex ion part is negative. If the complex ion part is positive, it's all good. It's just a regular metal name like you normally would do. A lot of fun rules with this, perhaps. So let's take a look at some of these names of these ligands, and we'll kind of see how we could go through these names. So here are some ligands. So as you can see, aqua or aquo for water, amine, methylamine, and then there's our sort of halogens: fluoral, chloral, bromo, iodo, hydroxo and cyano there for cyanide. And here's what I was talking about. If the complex ion is negative, sort of those older metal names: ferrate for iron, cuprate, plumate, argentate, arurate for gold. So call those guys in an 8 and kind of the older sort of name of it, if you will. Here's a few more examples of some ligands. We have hydroxide, which is hydroxo, carbonate, which is carbonato, a little oxalato. I feel like I'm ordering coffee. There we go. Carbonel. So these are some of those. Oxide is oxo, nitro for nitrite, and there are some of those. So let's just see. Let's take a look at the one that we did before there. Which one of those, right? So we have KAU OH4. So we have, whoops, KAU OH4. And then we had chromium NH3 6, I believe, and NO3 3. All right. So why don't you give it a try first, see what you're doing and what we should be doing on these. So first off, we did this earlier. We saw that this is our counter ion, which is K plus. And we saw that earlier here, our gold had a +3 oxidation state, and that led to a negative overall because of the -1 charge that's going on there. So, by the way, first off, the coordination number for this complex ion would be what? The coordination number here would be, it would be 4 in this case, as hydroxide is monodentate, so there's 4 of them attaching to the metal through the oxygen. Now, we can see here that the complex ion in this case is negatively charged, which means we are going to go with kind of the older way of naming gold. But we're going to start like a normal ionic compound, which is pretty much the counter ions are just named by their name. So regardless of how many you have of them, Just like, for example, if we had K2O, you would call that potassium oxide. It doesn't matter, there's two of them. Same idea here. So the K there is just going to be potassium, right? It's just the name of the counter ion. Now, we do need to name our ligands first. So our hydroxides are ligand, and there's 4 of them. So the prefix for 4 is tetra. And here, hydroxide is hydroxo. Now, we are going to go, because this complex ion is negative, with the older way of naming gold, which is right there. Rate is what we want to use. And we do want to put a Roman numeral to indicate the charge there on the metal. And it does come at the end of the complex ion part of the name. So this would be potassium tetrahydroxoaurate 3. Yeah. Any question on that name there? Now, if we take a look at this guy, as we saw earlier, this is our complex ion. And it has a positive 3 charge, as the chromium here has a positive 3. And obviously our nitrate here is our counter ion. In this case, our coordination number is going to be 6 in this case, as each of the nitrogens on the NH3 are monodentate, and there's 6 of them attached directly to the chromium in this case. Now, because the complex ion here is positive, we can use just a regular name for chromium, which is chromium. So we'll just use the regular name. We are still going to start with the ligands here. And we have ammonia, which is amine, and right there. And we have 6, which is hexa. So this is going to be hexaamine. Now we're going to go with our metal, which is our complex ion part of the name. Chromium, Roman numeral 3. And once again, when we come to our counter ion, even though there's multiples of them, we just use the name of it, and that would be nitrate in this case. So this would be hexaamine chromium 3 nitrate. Questions on that there? And this is what we're talking about in terms of the metal always comes at the last part of the complex ion name, not necessarily the last part of the name. This part here is the complex ion part, and that is the metal part at the last part of it. But here, because our complex ion is positive, this is the complex ion part of the name, and our metal comes at the end of the complex ion part of the name. Again, not the end of the overall name in this particular case. Any questions on that there? By the way, if I just had the ion by itself, so for example, if I just had the ion part without the counter ion, we would name this pretty much just the last part of the name. This would be tetrahydroxoaurate 3, and then we would just put ion at the end of it. So basically the same name, just slap ion in part of it. If we were naming this guy, it would basically be this part of the name with ion at the end of it, basically. So you basically name, if you just have the ion by itself, the exact same way. You just don't put in the counter ion name to it. Any questions on that there? Okay. Then why don't you try this one here? We'll do this one that's listed up here. It might be different than what's on your notes. So try this. Okay, so let's take a look. So once again, this is our complex ion part. And by the way, just from where it is placed in the formula, we know that it is actually going to be negative because it comes second. And the counter ion here is going to be positive in this case. By the way, we want to figure out perhaps the oxidation state there on the chromium. That is oxalate, which is -2. And there's 3 of them, gives you a -6. There's 3 potassiums, which will give you a total of +3, as each one is +1. And that gives me +3 -6 to balance that out to 0. That looks like a +3 in this case as our oxidation state there for the chromium. By the way, the coordination number in this case is a number between 1 and 10. Anyone? It is actually not going to be 3 in this case because this is a bidentate. So that's that oxalate, right? To combine at both of those oxygens that we talked about. So it is actually 6 in this case. So again, this is what I was talking about earlier. Is not always going to be that bottom number. Again, especially if it is a bidentate. If it's a monodentate, it definitely will be the bottom numbers. But here you have to keep track for that. All right, so we got a negative complex ion. And in this case, that means we're going to go kind of old school for the name of the metal. For the counter ion, even though there's 3 of them, and by the way, there's 3 of them because when we pull out just the complex ion by itself, it has a -3 charge, and that is why there are 3 of these guys to balance it out, basically, and give us the +3 to counter that -3 charge that's in the complex ion. But regardless of how many counter ions we have, it doesn't matter for the name. So this is still going to just be potassium. Now, when we come to our complex ion part of the name, we do have 3, which you could go trioxalato, which is what our oxalate is called. Here, we would then need to go with a chromate in this case, as that's the name of it, with a Roman numeral 3. So a little potassium trioxalato chromate 3. As I mentioned before, oxalate also is one of those ones that is commonly tris. Is used that other sort of prefix, and it's really because it is a bidentate, so they will use tris sometimes with this. So this one is also an acceptable sort of answer to that question on that name there. By the way, I think perhaps the one that was on the paper was actually a hydrate, by the way. I think I don't remember what the water was. There's so many waters, so I'll go with it was 3 waters. Why not? I don't remember what it was. But you would name it the same way. You could go still potassium, trioxalato, chromate 3. And because this is a hydrate, you could go trihydrate. Trihydrate for the 3 waters. All right. That's how you name hydrates, right? Is hydrate for the water and a prefix for how many waters there are in that particular case. Just in case the name wasn't long enough, we could do that if we had a hydrate going on. Any questions on those there? All right, let's try a few more here. Just make sure. Here's also a table of some more of those metal. Okay, so let's see how we're doing. So we could tell again from how the coordination compound formula is written, we see our complex ion is first. That does tell us it's positive, and we do see our counter ion second, which tells us it's negative. In this case, we still want to kind of figure out our oxidation state on our metal. So that is water, which is 0. That is chloride, which is -1. There's 2 of them, which is -2. We also have a chloride on the outside as our counter ion, which is -1. So all that together will tell us that the chromium here is rolling with a +3 oxidation state. In this case, the overall charge on the complex ion is +1, which is why we have just one of those chlorides on the outside as the counter ion in this case. Oxidation state of this guy, not oxidation, coordination number of this one is 6. Yeah. There are 4 waters, each attaching in one place per water, and there are 2 chlorides. All those guys are directly attached to the chromium So you basically got chromium, water attached to the oxygen. And if I drew too many waters there, maybe I did. Then we'll change one of those waters to a chloride. There we go. And this overall thing, again, is carrying a +1 charge, and you have basically a chloride with it as a counter ion basically on the outside. So because the complex ion is positive, we could use the regular name. Here we have two chlorines, so that's a dichloral situation. We have four waters, that's a tetra aqua or aqua, your choice, whichever one you like in terms of it. We do want to put these ligands in alphabetical order. So the one that comes first is alphabetically. It is this one because we're looking at A versus C. We're not looking at the prefixes. So we're going to go with the A guy first there. So that's a little tetra aqua, a little dichloral, dare I say. That is going to be a chromium, Roman numeral 3, and to finish out the name nicely, chloride. Need a big piece of paper for that. That's a tetraaquo dichloral chromium 3 chloride. Any question on that name there? Crazy people that come up with naming these things, right? It's like 3 people in a room decided how to do it. All right, we're gonna actually want to write the formula from a name, so that's actually might be easier. So it basically tells you what you need to draw. By the way, I know in this particular case, my complex ion is positive because I see the metal part of the complex ion at the end of that name, and sulfate comes after it, which means this is my counter ion, basically, in this case. So I know just from the way the name is written, I got a positive and negative. Also, I know that complex ion is positive because the metal is just a regular metal name as well. So tris ethyl endyl diamine is that EN one. And the reason that, again, they use tris here is, as I was mentioned before, in the actual name of the ligand is a prefix. So the actual ligand has that di part of it. So they're going to use it. When you're doing the formula, you can either write the formula for ethyl endyl diamine, but it is commonly, even with formulas, EN is used as sort of an abbreviation for it. So it's perfectly fine to use both in the name and also in the formula. And tris means there's 3 of them. We have a cobalt that has a +2 charge, which is what the Roman numeral means. And we have a sulfate, which is a -2. So basically our complex ion part is this. A little CO, a little EN3. That means that our complex ion in this case, this is no charge. This is +2. That means that our complex ion is carrying a +2 charge at this point. And that's important to figure out because we need to know how many of our counter ions we need. And in this case, we would actually just need one of them, right? That will give us a -2 and +2. So putting all that together will give us our formula for our coordination compound that looks something like that. Yeah. Question on that there. By the way, the coordination number of this guy is? Yes, it is 6. That's a good answer there. And again, that is a bidentate ligand. So each of those guys are going to bind 2 places at the nitrogen, both nitrogens in each of those guys, and that will give you 2, 4, and 6 atoms directly bound to the metal. Question on either of those there. All right, a few more funness here. Let's take a look. Let's do names on those 2. Okay, so taking a look at this one, once again, we can see by the arrangement here, we got some complex ion here. And again, we know it's positive because it comes first in the formula. That would make the chlorides there on the end there are counter ions, which will be negative. Here ammonia is 0. We have -1 there. We got 2 chlorides on the back side there, which would be -2. That's going to give us a +3 for our cobalt. Coordination number on this guy is also 6. We got 5 there and 1 there, basically. And here we could just start with our ligands. So we got 5, which is pentamine. We got Cl, which is chloral. And actually, that is the order it should go, as A before C. So we'll do a pentamine, chloral. And again, we're just going to use cobalt here, regular name, Roman numeral 3. And it doesn't matter how many counter ions we have, we're just going to call it chloride there at the end. Pentamine, chloral, cobalt 3, chloride. Any questions on that one there? All right, but yeah, we actually don't use mono in this situation. So if you just have one, you just basically just use the name, no prefix and stuff. Yeah. Other questions? Okay. So on the bottom one here, and by the way, the complex ion here does have a +2 charge here. As that's -1, that was +3, so that has a +2 charge, which is why we have 2 of the chlorides there to balance it out. Here we do see the opposite effect here. We do have our counter ion actually coming first, which means it's positive. We have our complex ion coming second, which means it's negative. And in this case, we got -1 for the cyanide. There's 6 of them, gives you a -6. We do have a +3 for the potassiums. So that means here our oxidation state on the iron will be +3. Again, not always going to be +3s. We ran into a bunch of them in these examples, but they can be different numbers. So we're going to start with our counter ion in this case, which would be potassium. We're gonna go with our now complex ion part, and then we got 6 of them, hexacyano. And then we want to go with the older school name there of iron, which would be ferrate, and we still need the Roman numeral here. So a little potassium, hexacyanoferrate 3. Coordination number on this guy is going to be 6, as cyanide is a monodentate and will attach basically 1 per molecule. Any question on those there? Fun with names. All right, let's try these last 2 to finish it up on. Do little formulas for each of these. Okay, so let's take a look since we're getting to the end here. So we're just kind of going to build what we need to write. I do know that my complex ion is going to be positive here because I see the metal part of the name and the metal's regular name coming first. And we got our counter ion here. So triamine, amine is ammonia. So you basically got an ammonia and you got 3 of them. You have a bromo with no prefix, which means you got just 1 of those. And you got a platinum. So if you're building your complex ion, it's a PT. You got an NH3, 3, and a Br. We have a chloride, which is our counter ion, which is negatively charged. So we do want to kind of figure out what the charge on the complex ion is. So that is +2. That is 0, and that is -1. That means I have basically a +1 charge overall, which will tell me that I really just need 1 of those counter ions here in this particular case to balance it out. Yeah. First off, any questions on that one there? By the way, the coordination number on this one is 4. Yeah. 3 and 1 has a +2 charge, so commonly 4 is very common with that. So lastly here, we got potassium, which is our counter ion, and I know that is positive because I see a little cobaltate happening there with my complex ion on the back end. That's negative. And that means potassium is my counter ion. I got hexafluoral, which is 6 fluorines, and cobaltate, so with a +3 charge. So if I put my complex ion together, I got that, and I got an F6. You really don't need the parentheses, but I'll put it there, I guess. And in this case, if we just look at the complex ion part, that's +3. That's basically -1, and there's 6 of them. So overall, our complex ion here is actually a -3. That means that we would actually need 3 of these guys here to balance it out, and that would give us K3COF6 in this case, yeah. Coordination number on this guy, also a 6-pack there, yeah. Any questions on that there? All right, we will wrap that up for today.